water, light. We need a wave model to explain the behaviour of all these things. But the wave model won't explain all of light's behaviour. As we have seen, sometimes light behaves like a particle.
Disgusting blob. I'm gonna have to hold it myself.
I love the film Ghostbusters. Maybe if the green ghost Slimer is a wave, then that would explain how he passes through walls. Now how do I get out of there? De Broglie said that matter could have a wavelength, and this is how he defined it. So let's find the wavelength of this ball. Momentum is mass times velocity. The mass of our ball is 160 grams. Let's take the speed to be 2 meters per second. The answer we get is small. I mean ridiculously small. This number of times smaller than the diameter of a proton. So this is solid and not a wave. So what is this de Broglie on about? Particles can behave like waves? Clearly not. He's being silly. Well, let's take another look at that equation. Surely if we took something with a very small mass, the wavelength would be longer. With this apparatus, I'm going to use a high voltage and eject some electrons from an electron gun at this end. The electrons will pass through a salt crystal located in this disc just here. If electrons do indeed behave a bit like waves, they will diffract as they pass through the small gaps in the salt crystal, and we will see a wave-like diffraction pattern up here on this screen. Right, I've turned the lights off. Let's see what we get. This diffraction pattern shows exactly the same effect we would expect if this was waves with a wavelength like X-rays. So let's look at the maths. The mass of an electron is 9.11 times 10 to the minus 31 kilograms. And let's say it's travelling at 2 times 10 to the 6 meters per second. Well, we find that it's got a wavelength just like that of X-rays. Remember though, unlike an electron, an X-ray photon travels at the speed of light and has no rest mass. So an electron can behave as a wave and as a particle. That's what we call wave-particle duality.